And welcome to today's webinar entitled Navigating Complexities in Distribution System Impact Studies. We're thrilled to have you join us for what promises to be an insightful and engaging session focused on evolving challenges and considerations in modern distribution system impact studies. My name is Tad Kane, and I'll be serving as your moderator and administrator for today's webinar. I'll be here to help guide the discussion, manage your questions, and just ensure everything runs smoothly. So before we dive into introductions, let me give you a quick overview of what today's presentation will cover. We're going to begin with a brief background on RLC engineering, just to give you context on who we are and what we do. And then from there, we're going to transition into technical content. We're going to start with a look at traditional impact studies. Then we're going to move into the details of protection study. And finally, we're going to explore the intricacies of EMT, or what's known as electromagnetic transient studies. And then we're going to wrap things up with a Q&A session where our presenters will respond to the questions you've submitted throughout the presentation. So we're, of course, fortunate today to have two highly respected professionals presenting today. First, I'd like to introduce Asa Sproul. He's a PE, a principal power system engineer here at RLC, whose extensive experience in technical leadership will make him a trusted voice in the field. And joining Asa is Michael Hannestead, PE, senior power system engineer with a deep understanding of system impact studies and interconnection analysis. So together, Asa and Mike will be walking us through the complexities, methodologies, and the practical considerations that engineers face when evaluating the impact of new projects on distribution systems. Just a little quick housekeeping note, professional development hour, PDH credits will be issued to all attendees who are joining us live for the full session. So just be sure to stay with us through the end. And with that, let's dive in. Asa, I'll turn it over to you to get us started.
All right. Thank you, Tad, and welcome to the presentation, everyone. I'm going to start with a quick company overview. So RLC Engineering is based out of Maine, and we have three primary offices, namely in South Portland, Hollowell, and Bangor. We're broken into three engineering groups that you can see here, with multiple subgroups in each group. And I won't read all of these services off, but these are the general areas for your reference. And we have just under 150 employees currently. So for our distribution studies experience in particular, to date, we've conducted over 500 system impact studies, or SIS, which is what we'll be discussing today. And these are comprised of what we call standard or traditional studies, protection evaluations, and electromagnetic transient, or EMT studies, as Tad mentioned. This presentation will go into depth into each of these areas. But aside from our SIS experience, we've also done over 100 detailed design studies, which are specific to the DER interconnection process. And namely, those are protection coordination studies, or PCS, for in-depth protection analyses, as well as VoltVAR operational studies, or VIVOs, for VoltVAR setting optimization for DERs via quasi-static time series, or QSTS. Some other studies, as you can see here on this list, are hosting capacity, integrated resource plans, 8760 curtailment analyses, novel device modeling and testing, flexible interconnection studies, and many more. So anything studies related, we can figure it out, and we're getting more and more interesting requests each day. So just a quick background on the presentation. So on top of the SIS we've performed, we've also seen and reviewed many different utility SIS on behalf of DER developers, which is another service we offer in order to help developers navigate complex interconnection processes. These typically include considerations for thermal loading, voltage levels, voltage fluctuation, protection, risk of islanding, or ROI, and ground fault over voltage, or GFOV. But despite having similar items, corresponding criteria, evaluation techniques, and mitigation methods are not always consistent. So this presentation covers what RLC believes to be best distribution SIS practices based on what we have firsthand experience with. And on that note, I'll now pass the mic over to my colleague, Mike, to begin the technical discussion.
Thanks, bud. So this slide's showing the typical, actually, before I get too far, can you hear me? All right, perfect. So this slide's showing the typical system impact study, or SIS, process that RLC usually follows. As shown, it's going from kind of least complex to most complex. And that also follows kind of most adopted to least adopted within the industry. So first, we're going to be taking a look at the traditional study elements. These are the elements that you will typically find in most system impact studies. It'll cover things like thermal, steady state voltage, voltage fluctuations, reactive power, and some of the screens. We'll then look at protection evaluations, and that might include effective grounding, fault current evaluations, project path devices, percent of pickup, reach coordination, and GSU inrush. I'll be covering traditional study and protection study, and then I'll be turning back over to Asa for the EMT or electromagnetic transient portion of this. And he'll cover things like inverter model validation, DER site modeling, distribution network modeling, TROV or transient overvoltage, ROI, risk of islanding, UFLs, under frequency load shedding, and VVI, volt var interactions. As you can see, there's a lot of different topics that we're going to touch on here. We can't go super in depth into all of these. Not to give a spoiler, but there will be a poll coming out right at the tail end of this where you can give feedback on future webinar topics. So if you feel like we hit something at a really high level and you would have liked more depth in that, jot it down off to the side. And that's something that you can drop into the poll at the end. So with that, let's dive into the traditional study elements here and look at thermal. So the test process for a thermal evaluation is to typically look at the boundary conditions. We look at a snapshot of peak loading, 0% generation. And if you have batteries on the system, we would also look at a maximum charging scenario potentially. The other snapshot that we typically look at to kind of bookend this is the maximum export scenario, which would be a light load, 100% generation, and max discharge if there are any batteries. Now, the caveat there is we do include and take into account what the developer wants as far as an operating scheme for the battery. However, if that's not specified, we'll typically look at worst case conditions. Another thing to keep in mind when looking at thermal evaluations is some utilities will include N-1 conditions, which is essentially loss of an element in the system. Usually for a system impact study, that is looking at loss of a specific load pocket because that load is going to offset a portion of the generation. And if you lose that load pocket, you're going to see a greater export condition. So you're going to see higher thermal loading on some of your equipment. You'll typically evaluate this on a substation level. So if we look at the simple graphic over here on the right, you can see that feeder C on the rightmost circuit has a generator. So from a substation perspective, we might look at loss of feeders A or B. We're reducing the load and increasing the export through that transformer. You can also evaluate this on a feeder specific level where you're losing some lateral load pocket that doesn't include generation, and you're increasing the amount of generation flowing through that circuit. For limits, it really depends upon the utility. Common limits we see are about 100% of transformer base rating or 90% of the conductors. And for mitigation, that's usually the equipment upgrade for where those violations occur. This is kind of an interesting topic. Voltage levels or steady state voltage evaluations. This is usually viewed as a pretty straightforward topic, but there is a stumbling point that we've encountered on a number of occasions. You will typically look at peak and light load conditions with and without the DER. But one thing that we've found is important is looking at the top and bottom of your voltage regulation bands, what we affectionately call TOB and BOB. So why it's important to look at the top and bottom of your regulation band is if you look at the simple graphic over here on the right side, this is kind of portraying a voltage regulation band of an LTC or a voltage regulator. You have a number of tap positions that's falling inside of your voltage regulation band. And when you run a simulation, that load flow simulation is going to find one of those tap positions that falls within your regulation band. But it doesn't necessarily dictate which one of those it's going to hit. So under normal load flow operation. Maybe it lands on 2, maybe it lands on 3. There are other types of load flow settings occasionally included within software that allow you to specify the highest or lowest tap position within range. That will present usually a more conservative landing point for that tap position. But as you can see, there might still be an area of margin between that highest tap in range and the absolute maximum voltage that could be seen within that regulator bandwidth. What we found is if you're not running absolutely at that top of band or perhaps bottom of band, depending on the scenario you're looking at, there's this window of risk where you might be missing a high voltage concern. And we saw this come up with the utilities where they would have gone out to do a witness test. They end up seeing high voltages that didn't show up during the system impact study. And they come to us with the system impact study, the model, and then the operational data from the witness test. And they're like, why are we seeing this in reality, but we didn't see it in the model? What we've often found was the system impact study was run without the top and bottom of regulation band considerations. And when they were looking at it in the field, it just happened to be operating at a higher point within that regulation band, and it was missed. So it tends to have to be kind of go back, see what adjustments need to be made in order to secure the case so that they can actually go back and interconnect reliably. Now, as far as the limits, those are pretty typical. 105% high voltage is common, 97.5% for low voltage kind of limit threshold is common for medium voltage systems. If you want to mitigate, load balancing is a good place to start if you have a lot of imbalance within the system that the DER is attempting to interconnect to. You can adjust or remove capacitors potentially, add or adjust regulator settings, off unity power factor, so fixed leading, volt var, etc., or increase system stiffness. So that's the reconductoring or substation transformer upgrades. For voltage fluctuation, these are where output drop tests tend to come into play. For PV, we typically use a 75% output drop due to really simulating cloud shading. For battery energy storage, it really depends what you're going to be looking at. And it depends on how that battery is going to be operated. You might look at the conservative scenario of 100% discharge to 100% charging. So that's a 200% change in output for that battery. Or we might look at just the transition from 100% discharge to 0 or 0% to 100% discharge. And it depends again on what the developer and utility have agreed upon as far as how that device is going to be operating. The limits, utility dependent, 2 to 3% is a common criteria we'll see. And things like off unity power factor can help with these. So fixed leading, volt var, StatCom's not on this list, but that can also be a mitigation, increased system stiffness, reconductor, substation transformer, things like that. This is another interesting one. We occasionally see rapid voltage change come up within system impact studies. This is not something that we typically evaluate because it's not typically a concern for modern DER interconnections. IEEE 1547 states that RVC shall apply to sudden changes due to frequent energization of transformers, frequent switching of capacitors, or from abrupt output variations caused by DER misoperation. It is not intended to address issues associated with slow voltage variations, which can be caused by cloud shadow passage and wind speed changes. Oftentimes, if we're reviewing a third-party system impact study and RVC is included, it's usually included to assess things like these slow voltage variations, which is not technically the intent of rapid voltage change. So that's kind of an important consideration. And where it's most important is when you're considering mitigations. There's a lot more mitigation options for alleviating or ameliorating the slow voltage variations versus the rapid voltage change, which usually happens over a 1 second period. Regulator operations, this is another output drop condition that we're looking at. We're typically looking for tap operations to be less than or equal to 1 tap for a given transition, or the other common utility practice we'll see is 50% of the regulator bandwidth. Now, it's important to consider here that if you're looking at 50% of the regulator bandwidth, you're usually looking at the terminal voltage of that regulator. And if it is operating within a load drop compensation scheme, the terminal voltage of that regulator is not representative of the number of taps that it may see. So if you have load drop compensation schemes on your circuit, it can be better to actually look at the number of tap operations that are occurring rather than using like a 50% of regulator bandwidth criteria. It's just a note. Mitigation, you can adjust the settings sometimes. You can use off-unity power factor, so fixed leading, volt var. You could add potentially a StatCom to help regulate the voltages a little bit, or you can increase system stiffness with reconductor, substation transformers, etc. For the reactive power evaluation, this is a pre to post project scenario. It's typically only evaluated if you are running off Unity or if you have other projects prior to this that are running off Unity. And you look pre to post project, we typically run this under top of band or tub to simulate worst case VAR draws if you have volt VAR systems or volt VAR DER that are operating within volt VAR on your system, because that's going to present the highest system voltages and the most reactive power that you'd be absorbing. So you'd look at reactive power measured at the substation POI and potentially other previously queued DER sites, and you would size your reactive compensation accordingly. The reason why you're looking at other previously queued DER sites is you need to make sure that the DER that is being added to the system is not increasing the burden on those previous sites. It's entirely possible that you had previous sites operating in volt VAR. You go to study this one at Unity, it passes all of your voltage checks. However, it's actually increased the burden on those previous projects. It's the previous projects that picked up the regulation and voltage suppression of that new project. So by looking and ensuring that those other previously queued projects have not increased their VAR burden, you're ensuring that the new project is essentially picking up its own share of mitigating the voltage rise. One interesting complexity here is if you are a utility that has a subtransmission network, so let's say particularly a 34.5 or 46 kV network, so one of the lower voltage subtransmission systems, the amount of power that's being exported can cause high voltages on your subtransmission system. When you absorb reactive power locally, you're pulling that reactive power off of your subtransmission, which can help mitigate the high voltages that are occurring on your subtransmission system. If you then put switch capacitors outside of your substation, let's say, you're likely fixing the issue on your distribution system. However, you've now compensated for that reactive power that was being drawn from the subtransmission, and you might have just put those kind of high voltages back onto that subtransmission. In those cases, you may need to compensate with a more dynamic device and have a StatCom on your subtransmission system to more dynamically compensate for the really changing system conditions. So that's something to consider if you're a utility that does have a subtransmission system. Load rejection over voltage. Here, the process is really just looking at the generation to load ratio within the islands. It's usually a pass or fail screening criteria. Most typically, generation to load ratios less than 2 pass or greater than 2 fail. Ratios up to 10 may be mitigated with HECO Rule 14 Appendix I certification. And PSCAD or other EMT simulations can be used to evaluate LROV and GFOV concerns. One thing to note is we have seen instances where projects passed either due to the generation to load ratio or they were mitigated by HECO. However, they failed once they got to the EMT simulations. Now, it's hard to say whether that was because the EMT model wasn't necessarily representative of the actual device, or whether they did in fact fail these LROV concerns. But something we've taken to do is, if we're already running the EMT simulations, even if the screen passes, we will sometimes double check these LROVs. Similarly, for a risk of islanding screen, depends on the utility. Often it's some form of the old Sandia screen, which involves real and reactive power balance checks, looking for large synchronous generators, which might stabilize the frequency within the island, looking for dynamic voltage regulation, such as volt var. And it's a pass or fail based on the screening criteria being used. We usually recommend a PSCAD or other EMT simulation to more accurately evaluate the risk of islanding. If EMT is not being entertained by that utility, it may require DTT as the mitigation. Asa will talk a bit more about that, though. Okay. So that was me plowing through the traditional study. And next is the protection evaluation. I'm going to try to give myself about 7 minutes for this, so we might move a little quickly. But for effective grounding, we will typically isolate the DER facility, which removes the ground source, and then we evaluate positive and zero sequence impedances or unfaulted phase voltages if we're looking at the coefficient of grounding methodology. The coefficient of grounding method is typically used for systems with a lot of inverter-based resources. The traditional method looked at zero sequence reactance to positive sequence reactance and zero sequence reactance to positive sequence resistance. If there are concerns about GFOV, we'll typically look at this in PSCAD or EMP simulations, and it's a good way to confirm the size of any effective grounding devices that we might need to add to the system. For fault currents, we will measure the increase in 3-line of ground and single line of ground fault currents on the system after adding the DER. Most typically, this is a pass or a fail screen. Common screening criteria we see is if it's less than 10% increase on the substation or the point of interconnection, and this circuit that we're looking at wasn't previously flagged as being close to a limit, then there's limited additional evaluations. Some utilities also require just looking at the protective device interrupting ratings and making sure those are not being exceeded. Depending upon what the practice is, you'll either fail the screen and then move towards the more detailed protective device rating, or if you already conducted that, you would replace any devices with insufficient ratings. Project path devices, this is looking at or for any single phase operating devices between the substation and the point of interconnection. So that's the project path. We'd be looking for fused laterals or fuses within the project path, single phase operating recloses, etc. The criteria is usually that those need to be removed and they need to be replaced with either single phase operating, they need to be replaced with gang operated units or relocated beyond the project path. So if your project is right below a midline recloser that was single phase operating, you might be able to just shift that down. Or if your project is right below a fuse, that fuse might be able to be relocated just downstream of the project without the need of a new device, assuming it's not impacting reliability. Now, percent of pickup is an interesting one, and this is where we see a lot of impacts from DER interconnections. For this, we would look at the reverse current flow at all upstream devices under the maximum generation export scenario, so light load maximum generation. A typical criteria we see is that reverse or the reverse amps flowing through the device should be less than 67% of the minimum pickup. So if we look at the example over here on the right, we have a midline recloser labeled B. The minimum pickup on that was 150 amps, which means anything approximately 100 amps or less would pass, and anything more than that would fail. And just as a idea of size, on a 12.5 kV circuit, that's about 2.2 megawatts of generation. So it doesn't take a whole lot stacked up behind some of these devices to push you over that minimum pickup. And then that's where you start getting into more protection adjustments that you might need to make. So here we see mitigation being increasing that minimum pickup. If you can't increase that minimum pickup for any number of reasons, you might need bidirectional trip settings now. And that could mean replacing some of those devices such that they'll have that capability. Now for reach, what we typically see is the biggest impact to reach is if you had to go and adjust one of those minimum pickup settings. If you didn't have to adjust any of those minimum pickup settings, we tend to find that the impact to reach is pretty minimal. To look at this, we apply a fault at the end of each zone of protection and assess the available fault current relative to the device pickup settings. A typical kind of representative criteria that we see is that the available fault current at the end of the zone of protection should be 2.2 times greater than the device pickup. We occasionally also see kind of a high impedance fault being applied at the end in ensuring that the upstream devices can actually detect and trip still. A device relocation could be an option, shifting one of your devices closer to the end of that zone of protection, or additional devices may be required. Coordination. So device coordination is analyzed to ensure all project path devices are still coordinated and maintaining sufficient margin. One coordination method is outlined in the Cougar Power Systems electric distribution system protection, but it tends to be utility and methodology dependent as far as approach and then the limits that are applied. But typically it involves ensuring the minimum time separation between your coordination curves and then adjusting settings or adding devices kind of as needed to maintain those coordination requirements. And then my last slide here would be GSU inrush. We usually apply and look at the DER GSU transformers and evaluate it based on IEEE 242-2001 standard inrush multipliers. And the inrush must not trip the upstream protective devices. If we see that it is tripping upstream protected devices, I would say in a very small amount of cases, we may be able to shift the settings of one of those upstream devices. If it was a really borderline case, usually it's not. And if it's not, then we might be able to look at detailed analysis of manufacturer inrush current information, if that's available. We could look at staggering GSU energization. So if you have a facility with multiple GSU transformers, if a single GSU transformer is not causing any kind of protective device coordination tripping concerns, then you might be able to look at staggering the energization of those GSUs. Or you might need to look at introducing an impedance into the closing of those GSUs to limit the inrush current. All right, I know I flew through all of that. That was a lot to cover. Looking forward to the Q&A, but with that, Asa is going to pick it up from here and discuss some of our experience with the EMT studies. I'm going to give up remote control.
All right, thanks, Mike. As Mike mentioned, I'm now going to take you through the EMT study considerations, which are often screened for, but a lot less often evaluated. So the first thing we do is inverter model validation, as it matters a lot to the project design. So our first step here would be verifying the necessary documentation, which is largely comprised of OEM, user manuals, and compliance checklists. These may be specific to the utility, though public documents are available, such as those released by ISO New England and Electronics. From there, we would ensure that the provided model meets the requirements, and here are a couple of examples listed here. So the first one represents the full detailed intercontrol loops of the power electronics, preferably using embedded real code. And what real code means is the code used in the inverter firmware and the actual field installation is represented in the PSCAD model. This is hopefully always the case, but in some cases it's not, and that's what these checklists are aiming to ensure. that they're a close enough match with reality. Another requirement would be includes all pertinent protective functions such as passive loss of mains detection or LOMD, instantaneous overvoltage protection, etc. From here, we would ensure that the model parameters match what's in the provided user manuals or data sheets and manuals. So for example, do the real and reactive power output characteristics or PQ curve match the performance that's within the PSCAD model? And from here, we perform some standard performance validation tests, including fault ride through, voltage and frequency response, protection verification, and some others. Once the inverter model has been validated, the DER site model must then be created within our model. So the following parameters would typically be included. First up would be relay protection, collector system equivalent impedance. If you can see my mouse, I'm kind of circling where those are at in the model here. Project inverters, and these are often aggregated if they're all the same inverter, but sometimes if a site has multiple types of inverters or they're operating at different ratings, we'll model them explicitly to ensure that accuracy is captured. If there are any surge arresters contained within the design, we'll model those. Any grounding transformers or other forms of effective grounding like neutral grounding reactors will be included here. And then an aggregate GSU or generator step-up transformer. And same methodology here. If they're all the same GSU, then we'll aggregate them. But if you have a couple of them and they have different windings or ratings, then we'll model them explicitly. Once the DER site model is set up, a distribution system model is required. And the following would be included. That's outlined here in this diagram. So the source equivalent, or the equivalent of where we're tapping into the subtransmission or transmission system, the individual feeder topologies and impedances, any capacitor banks and their associated controls, whether those be fixed, switched on voltage, timed, etc. Substation transformer, any project bounding breakers or reclosers, and I'll discuss the importance of those here shortly. Voltage regulation, such as transformer LTCs, bus regulation, and line regulators. Adjustable per phase loads. So we do unbalanced load modeling here per the provided distribution network model for accuracy's sake. And then any other DER that's located with the model. So if it's IBR, then it's typically going to have a PSCAD manufacturer model provided. If it's a rotating mass, typically we'll use some built-in models, but get the specific parameters for that particular generator. And I would also note that these PSCAD models are not often, I don't think we've ever had one provided from a utility, but we do get the GIS power flow models from, Symes, Synergy, Windmill, et cetera. So we've developed techniques for extracting and automating this model creation process to really improve efficiency there and cut down on study time. But with modeling established, let's get into the analyses. So first up, we have transient overvoltage, or TROV. And this is evaluated per IEEE 1547-2018, section 7.4.2, limitation of cumulative instantaneous overvoltage. Wow, that's a mouthful. I'll only say it once. But effectively, cumulative voltage durations are measured per this graph shown on the left from 1547 and held to the criteria of limits shown on the right. And it's a little confusing, but by this I mean these blue horizontal lines here on the left correspond with the various magnitude thresholds that are shown here on the right. So 2 per unit, 1.7 per unit, 1.4, et cetera. The durations that each threshold is violated are summed. So in this case, that would be this X, this Z, and this Y. And then you essentially obtain a performance curve on how your project performed under those scenarios. And I'll show an example slide shortly to give you an output of what our evaluation would provide. But for this evaluation, both line-to-ground and line-to-line voltages are monitored. And these are measured over a 1-minute time window per 1547. So there are two components to TROV that we test. The first is load rejection over voltage, or LROV. And this test process involves posturing the case with maximum generation and light loading, and then testing the potential island. So the limits, as I mentioned, are 1547, 7.4.2, and some tools we have in our toolbox to mitigate any violations are first, inverter transient overvoltage protection, or TOVP, or self-protection over voltage, or SPOV. These are largely the same thing, and manufacturers may implement them in different ways. I think SPOV is actually a more popular term these days. But again, they're largely the same thing, and they're kind of the no-cost solution as they're implemented right in the inverter firmware, and don't typically require external devices. Before external devices, we have the option of implementing additional surge arresters, and that's been shown to help. So the second component of TROV is ground fault over voltage, or GFOV. And this test process involves the same case posturing as LROV, but in this case, instead of a no-fault open of a protective device, we apply a single line to ground fault at the project point of common coupling, or PCC, for several cycles before the device immediately upstream opens. And we could make that assumption at this point in the study that that device would open because we would have already ran coordination per Mike's discussion. Same limits, 1547, section 7.4.2. And the mitigation strategies, 2 out of 3 of these are the same thing. So inverter SPOV, either enabling or tweaking to those settings, or surge arresters. But one additional tool we have is modifying the effective grounding design. And that's been shown to help. So effectively what you would do is reduce your zero sequence impedance path to ground. And again, that's been shown to mitigate GFOV in many scenarios we've encountered. So as promised, here's a quick example of an output of one of these tests. So what's shown here in this graphic is 3 different traces. So the red is what I showed you a few slides ago. That's the 1547 criteria. This blue trace is a project PCC before any mitigations go in place. And the reason I say before any mitigations, as you can see in this zone here, we're actually above this envelope that we're trying to hold the criteria. So that's a violation of this testing, right? So in green, however, some mitigations were implemented, whether it be SPOV or surge arrestor implementation, and we're well underneath this envelope here and passed this test and don't require additional mitigations following that. So our next evaluation within the EMT study would be risk evaluating, or ROI. And this test process involves creating scenarios where real and reactive flows, or P&Q flows, are as close to 0 as realistically possible within the bounds of the actual loading on the system. So we're not going to create an unrealistic scenario, but we'll use kind of the worst case scenarios that could result in this. And we do this across any potential island. So the limits here, 1547, 2018, but section 8.1.1, their 2-second cease to energize and trip requirement, which I'm sure many of you are familiar with. And our mitigation strategies for this are, if it's possible, we would adjust the inverter loss of mains detection settings, which are used for essentially ROI mitigation. I would note that, and if I haven't noted it before, these inverters are typically going to be black boxed, meaning that all the control functionality is there, but what we can actually see and what we can actually control within them is very limited because manufacturers want to protect their IP and not provide that to everyone. So LMMD settings in particular, if we have access to them, it's usually just, can we enable them or disable them? And we would just enable them in this case. However, we have had success in the past reaching out directly to manufacturers through our contacts and getting them to make tweaks to these settings and update their models, provide us with new ones, and then we can retest. Now, I would say if they do anything to mitigate ROI in this case, they would also need to implement that into their firmware for their field installation, so we're not simulating something that's not going to be available in real life. Our second mitigation strategy, the one most of you are likely familiar with, is direct transfer trip, or DTT. Now, I would say you could go through this full EMT study and ROI process and still require DTT. But in our opinion, it's a lot better to run the full study rather than requiring this by default or based on the outcome of a screen. And to add to that, some statistics, based on what we've studied, all the projects we've studied, only 7% of projects that failed the screen resulted in failures upon the full EMT ROI evaluation. So a 93% pass rate is pretty good, in my opinion. And just to give you a quick picture of what we'd actually be simulating here. So on the right is the same exact project model I showed a few slides ago. On the left, you have 2 reclosers that are circled in green. So this first one here is the feeder recloser that is responsible for providing protection to the entire feeder. So we would get the P&Q flows as close to 0 as possible here, trip it, and then see how the project performs. And then we would repeat that exercise for this downstream line recloser. Now, to add some color to this, I provided a few example plots here directly from PSCAD. So what you have here on the left is SS, which stands for substation, VRMS or RMS voltage. And then you also have P, real power, and Q, reactive power. Those same three parameters are captured at the POI or the project point of interconnection. So what's captured in these specific traces is you have an event at 3 seconds, which would effectively be one of your upstream protective devices tripping. And then at 3.5 or 0.5 seconds later, the project actually trips offline, and you can see that the voltage goes to zero as you would want to happen under a fault condition or your protective devices opening. However, in contrast, on the right here, we have the same event at 3 seconds, but you can see at 5 seconds, you still have voltage, and that would indicate that your project hasn't tripped, which would also mean you failed your 2-second run-on time criteria per 1547 and would require mitigation either through changing LOMD protection or direct transfer training. Our next evaluation, under frequency load shed or UFLs, which is really fun to say. So a brief background on this in case you're not familiar, but distribution feeder breakers are often equipped with UFL settings such that they can shed load during transmission under frequency events, which could be caused essentially by on your transmission system, you have too much load and not enough generation, so you have to shed load to not cause an under frequency event. With that said, the reason we evaluate this here is projects may pass the ROI evaluation, but fail UFLs due to pickup times from the UFL settings that are less than 2 seconds or cause other adverse interactions with the UFL settings. So we aim to ensure that DER doesn't cause UFLs nuisance tripping, as these devices can become locked out, require manual restoration, and in general, for protection philosophy, you don't want devices tripping on things that aren't actually happening. So this test process is fairly similar to ROI, but with more sensitivities to load to create conditions where the project may still be energized, but UFLs could trip that protective device. And the limits here, pretty straightforward, are that UFLs does not trip if it's not an UFL scenario. So mitigation techniques, the first two are the same as an ROI failure, adjust the inverter LOMD or require DTT. However, the third, you may also have to potentially move these UFL settings to another substation. So in general, this usually happens on feeders with a good amount of DER anyway, since the point is to shed load and not generation. And in fact, many regulators require UFLs relocation to ensure this does not happen. Now, I will say, based on our research, we've seen some utilities utilize smarter technologies that'll actually look at the net flow through feeder devices. And if you have a forward flow, which would indicate load, then you could trip. But if it's a reverse flow, which would indicate more generation than load, then you wouldn't trip. But again, those are a bit more sophisticated, and I don't know if many people are using them yet. But another statistic here, 15% of projects at UFLs equipped substations fail the full evaluation. So that's an 85% pass rate and still pretty good. So to give you a quick graphical example, hopefully this one is easy to understand, but on the left side here, you have that same event that I showed you for the ROI pass scenario a couple slides ago. So as a reminder, you have an event at 3 seconds, and at 3.5 or 0.5 seconds later, your project trips offline and it's not an issue. However, the right plots would indicate an UFL's failure due to a nuisance trip. So what you have up here, F-measure or measured frequency, and this horizontal red line is F pickup, or the under frequency load shed pickup, right at about 59.1 hertz or so. So essentially what happens here is if the frequency goes under this frequency pickup for a certain amount of time, then the UFLs would look to activate. However, there's one safeguard to this, which is namely voltage block settings, or sometimes referred to as voltage inhibit. So this second plot, one shows the 3 voltage traces for A, B, C voltages, as well as the voltage block setting here on this horizontal line. So essentially what happens is if your frequency goes below the frequency trip setting for a certain amount of time, your device will look at the voltages, and if they're above this voltage block setting, then your UFLs will activate. However, if they're below the setting, then it would effectively block, as the name would indicate, the UFLs from operating. And that's really a safeguard to ensure that you're not tripping on UFLs under normal fault events that could happen right local to your distribution system. Lastly, this is just a flag here at the bottom that goes from 0 to 1 that indicates that the UFL's picked up. And the thing to note here is that, again, event happens at 3 seconds, the DER trips off at 3.5, but the UFL's picks up before that 3.5. So even though we passed ROI from having less than a 2-second run-on time, we still failed the UFLs and caused nuisance tripping. Our last technical topic here, volt-var interaction assessment, or VVI. So this testing involves posturing the case such that DERs operate at a steady state within their voltage profiles. Then we apply some classic control theory and perform a step change that causes all projects to operate on their volt-var curves. And then we repeat the same exercise with a ramp change, and then observe the voltage and reactive power characteristics. So the limits here, one, ensure no oscillations or voltage hunting, essentially adverse control interactions between projects operating the volt-var. And then we use engineering judgment to determine if this response could create issues such as potential flicker impacts or device misoperation. The mitigation strategies, one, if it's possible, we would reduce the aggressiveness of volt-var settings, or essentially make the proportional response to a voltage deviation a bit less per adjusting the volt-var setting slope. That's not always an option because sometimes we're limited based on the traditional and evaluation that Mike already covered. So a second option would be to increase the inverter volt-var open loop response time. This is typically a 5-second window per 1547, but I believe they can go up to 90 seconds when still be in that criteria. But if you go too high, you also want to make sure you're coordinating with your tap delays of your LTCs, regulators, and switch capacitors if they're on the system. The third mitigation strategy would be applying a power plant controller, or PPC, that's properly tuned and can provide real and reactive power commands to the project inverters rather than the inverters doing it locally or through their terminal readings. And then just a quick example of results. So the plot here shown on the left is with no PPC, which was the mitigation used in this example. And you can see that this voltage here, VRMS, at the project PCC has some sustained oscillations at steady state. With the power plant controller, however, you can see that that's essentially a flat line, which is what you want. One thing I'd quickly note regarding PPCs is we have had experiences in the field where PPCs don't necessarily operate correctly and can result in their own control oscillations rather than fixing the issue when applied to projects with low POI short circuit strength. We've actually seen the same with inverters, so it's always important to ensure that your design has proper capabilities for the proposed application, as with anything else. But with that said, we hope you enjoyed this presentation on SIS topics. And before we move on to the Q&A, we'd like to quickly conduct a poll to see what topics would be of interest for future webinars. We've listed some options here, and I see the poll just went live, but you should be able to enter some other topics in that kind of second option if you're interested. So I think we're going to give attendees about 30 seconds or so before we move on to the Q&A, Tad. Is that correct?
That's correct, Asa. Yep, we'll give everyone just, like Asa said, just about 30 seconds. Please try to give your input. We're definitely looking to base our next webinar off of your poll input. So it'll be well appreciated. And like Asa said, if you've got some other ideas, you can put that down in the short answer. We'd really appreciate it. I see folks are great job here. We really appreciate everyone. I think we can move on to the Q&A. We've had some great questions from everyone. I'm going to select just a couple of questions here that I'm seeing. So the first question here to you, Asa and Mike, is how are the aggregate impacts of large amounts of DERs taken into consideration in the study process?
Yeah, sure, I can grab that one. So usually what happens, at least here in New England, is after a certain amount of DER is proposing to interconnect on a certain, whether it be sub-transmission network or radial, but enough to essentially cause a concern, that entire subtransmission network would be studied, and also the transmission that serves that subtransmission. So effectively what happens is that it would be the affected system operator study, or the ASO study, where we look at steady state, transient stability, short circuit, and EMT concerns within PSSE. So that's usually handled by our transmission planning group. And then once all those have been completed, we would aim to look at the kind of the full impacts at the transmission scale.
Okay, great. Next question we have here. PSCAD inverter models can sometimes take multiple iterations to get right. How does RLC work with all relevant parties to ensure properly functioning models?
Yeah, I'll snag that one as well. So typically what we aim to do is have good manufacturer contacts, and that can take, a few iterations to get the person that's necessarily in charge of updating the inverter models and is responsive. So that's usually our first path if we can reach directly out to them, and sometimes we'll need to loop the utilities in to make sure everybody has visibility. But if that's not an option, then sometimes we'll put the onus back on the developers to reach out to the manufacturer they're purchasing the inverters from. But in general, reaching out to manufacturers directly works very well.
Okay, great. We have a few other questions here. Kind of looking, a lot of great questions. Let's pick this one here. It says, for testing mitigation approaches, particularly involving both slow, example given regulator, excuse me, and rapid controllable components like smart DER functions, what is the QSTS simulation solution time step in different RLC traditional study?
So and Mike, feel free to jump in here as well, but for traditional studies, we're not often using QSTS. That's normally something we're going to use for 8760 curtailment or our Voltvar operational studies, which I mentioned is part of our detailed design process. But we use SIME primarily, and the lowest you can get on that time step is 1 second. Sometimes we'll increase that for efficiency, as long as it's, at least half of the fastest regulation device delay. So if an LTC has a 30-second tapping delay, then we'll simulate it 15 seconds, for example. But really, it's situational depending on what we're trying to find. And in general, when all else fails, especially if the simulations can move quick enough, we'll use 1 second, and that's largely proportional to how many nodes there are in the model.
Yeah, and I would say the only thing that I would add to that is we're often limited by data availability more than simulation techniques. So do we actually have good enough data to model the generation at those low time steps? And that's often the bottleneck we see. Sometimes we'll have to look at a specific geographical region and see if we have any other data that would be a good approximate of that might not be directly from that specific site or adjacent site or utility, in order to, essentially approximate it as best we can with the information provided, because oftentimes it's not available.
Okay, great. I think we've got 5 minutes. I think we have time for 1 or maybe 2 questions, and then we'll wrap up with our contact information and just let you know how we're going to follow up this webinar and how we'll be available. But there is kind of a nice question here that asks, is there a large difference in the associated durations to complete each of the 3 study options?
Yes, absolutely. Usually it's depending on the type of software you're using. So if you're using load flow software such as SIME, which we would traditionally do our traditional study or our protection study in, that's going to take a lot less time. EMT is going to completely depend on how many different inverter models typically you have in there, because those are the most complex component within those simulations. And earlier on in our process, those could take, hours to days to simulate, which could really bottleneck the process. If you run a simulation, see a violation, then you have to propose a mitigation and rerun it. It's going to take that time again to simulate it. However, more recently, we've developed some techniques for parallel processing and some more resource-intensive machines that can do these a lot quicker. So something that used to take days will now take, an hour. So it's a lot less of a bottleneck than it used to be. But in general, EMTs are a lot more complex and take a lot more time. But that said, all of the stuff that we're talking about here, we're normally able to complete in a 5-week time window or so. Really depends on the scope, but the scope we mentioned here is about that.
Okay, great. And I would love to squeeze this one last question in. I think it'll be probably a succinct answer, but a good question. If the inverter manufacturer adjusts the LOMD settings, like you mentioned, Asa, do they perform the UL 1741 test again?
That's a great question. I'm not sure I have the answer offhand, and Mike, feel free to chime in if you do. But in my opinion, they probably should, right? If they achieved that certification through that certain method and then changed their methodology, then they would likely need to be recertified.
Yeah, I agree with that.
Okay, great. We have 2 minutes left, which is going to allow us a little bit of time here. We have a slide up here with myself and Asa and Mike's contact information. You can, if you have questions, projects, anything, you can follow up, technically speaking, with Asa, Mike, or if you have just questions about RLC, anything, you can follow up with me as well. This webinar has been recorded. We have a webinar library at rlc.com at our website that you'll be able to access this to review the slides and the content. And we will be sending out, if we didn't get to your questions, I just want to let everybody know that we're going to be, Mike and Asa will be answering all of your questions, preparing that as a document, and sending that out to all attendees via your email that you registered with, along with your information on your qualifying PDH credit. And I believe that is everything in terms, unless Mike or Asa, I've forgotten anything, but I think that might be everything. Yeah, okay. And then finally, I just wanted to thank everyone for attending. We will be conducting more webinars throughout the year for multiple divisions. This is our Power System Study Division. We'll be putting on webinars for our Substation and Power Delivery Division, as well as our Power Gen, which might be benchmarking or mod studies, but stay tuned. And thank you again, everybody, and have a great afternoon. Bye-bye.
Yeah, thank you. Take care, everyone.
Thanks, everyone.